잘 들립니다.
네, 감사합니다. Uh, I'll start my presentation. My name is Heewoo Rho from EQS at KAIST, and today I'm gonna present variational quantum algorithms and combinatorial optimization problems. Before I start, uh, this presentation is for beginners since I'm not in CS major and I don't know much about quantum computing. So I and for the freshman in KAIST. So I omitted some equations and exact definition of mathematical terms. So hope you understand it. So this is the outline of my presentations. First one is the overview of the variational quantum algorithms, and we have I'm gonna introduce two algorithms that names QAOA and VQE, and the examples of combinatorial optimization problems as max cut problems and K-coloring problems. And these are case studies for QAOA for max cut problems and VQE for K-coloring problems and references. So what are variational quantum algorithms? So VQA, for short, is classical and quantum algorithm combined in one algorithm. So quantum part is parameterized solutions using tunable parameter theta, which explore the solution space. So these parameters are optimized to minimize the cost function I'll introduce later. And classical part is optimizers such as Cobila, LBFGS, and SQP. So these are examples of classical part. Adjust the parameters theta based on feedback from the quantum circuits measurements, driving optimizations. So why do we use VQA? Because these devices are noisy and limited in qubits that are in coherence. So VQA just mitigates hardware limitations by using hybrid techniques instead of a full quantum computing. So it reduces quantum circuit depths through classical feedback loops. So this is a framework overview. First, the inputs are answers and cost function and training data, and we feed it to the quantum computer answers, and we measure it, and we measure the cost function, and it calls to a classical optimizer, and it so it updates the parameter theta to ANSYS. So this is a iterable way. So ANSYS is a parameterized quantum circuit that prepares trial quantum states. I'll explain more about it later. And cost function is evaluates the solution's quality and forms up the optimization landscape. So we want to find the minima of cost function. And optimizer is to adjust the parameter theta to minimize the cost function. So this optimizer is in the classical computer and ANSYS is in quantum computer. And we introduce the cost function. The cost function C encodes the problems to be solved in mathematical framework. It creates we need to find the global minimum of cost function. So cost functions can be expressed as these equations below. So this is a generalized form, and f is some function, and rho k are input states from training set, and O set OKs are observables, and U is the parameterized quantum circuit. Next, we move on to the parameterized quantum circuit, which is ANSYS. It is a design quantum circuits used to solve a specific problem. The structure of the answers determines how theta are adjusted. And there are two kinds of answers, problem inspired and problem agnostic. Problem inspired is for specific problems using some knowledge such as physics or chemistry, like using some screwdriver is an analogy, a specific tool for a specific task. And agnostic problem agnostic tasks are general purpose structures, like using multi-tool for easy understanding. And general structure of answers is multiple layers of quantum gates. Each layer is unitary transformations, and each unitary operation is like this. And this HM is mathematical operator representing problem-specific information, and WM is additional gates that manipulate the quantum states. Then we move to the classical optimizer. So we can categorize in two types of optimizations. First one is gradient based. It's used as the gradient of cost function to adjust parameters. It's very fast for smooth differentiable cost functions. So we can differentiate and we find maybe the local minima, but we need to find some global thing. So the good thing of it is faster convergence, but it might requires differentiability. So we can stack, but we can stack in local minima. So that's the cons. And gradient-free optimizations, it works for noisy or discrete cost functions as well, but it handles noises very well, while it is more slower and expensive than gradient-based. And uh, I need to explain the QAOA, but we need to for easy understanding. First, I introduce some problems. So it's like max cut problems. So imagine you want to solve a very complicated puzzle, like dividing people into two groups so that the total number of disagreements between two groups are maximized. So it's similar to the max cut problem. So for example, it's like divides people into left and right wing in politics. And QAOA is like a smart assistant that uses both classical and quantum strategies to help solve such puzzles. So what is QAOA? So quantum approximate optimization algorithm. It solves optimization problems using the following steps. So for understanding, I just wrote this as a words, but if we know the exact process, if we want to know the exact process, we need some quantum mechanical equations, so many. So the starting point is make a superpositions. So considering all possible solutions simultaneously, so like flipping a coin for each options, this is achieved using quantum superpositions, applying Hadamard gates to all qubits. And rules of the puzzle, so it's a problem unitary. We apply rules, problem Hamiltonians, that score how good each arrangement is. So it acts as a checklist, ensuring those solutions are aligned with the objective. And we use also the mixer unitary. So it introduces randomness to explore alternative possibilities. So this prevents the algorithm for focusing on single solutions that is found too early, so we can get a better solution. Then we introduce the variational quantum eigensolver, which is a kind of VQA is designed for find the lowest energy state of a system. So how it works is quantum part, it tests potential solutions using a quantum circuit is an ANSYS, exploring many possibilities simultaneously, and classical part is adjust parameters to improve the solution. So this process repeats until the best solution, which is lowest energy, is found. So if we make some analogy, it combines quantum and classical strengths, like drones scanning a mountain of range, and GPS. GPS is classical part, guiding you to the lowest valley. Then we introduce the K coloring problems, which is solved by VQE. So K coloring problem is a puzzle where we want to assign colors to nodes in a graph such that node to connected nodes use a most K different colors that I think we're all familiar with the four coloring theorems. So it may be an example. And if we make an analogy, imagine a map where neighboring regions need to have different colors, and we aim to minimize the number of colors while satisfying this rule. So this is the way VQE solves K coloring. First, we represent the problem. Each node's color is represented as quantum state. The rule not to connected nodes share a color become a constraint. And cost function is it assigns a penalty when two connected nodes have the same color. So VQE minimize this cost to find the valid coloring. So optimization, the quantum circuit ANSYS explores the possible solutions, and classical optimizer adjusts parameters to find the lowest cost, which means lowest energy. So why do we use VQE for K coloring? So the advantages of it is it can explore many solutions at once because it has quantum superpositions, and it might be very efficient for many nodes for large graphs, and we can adapt the quantum circuit to suit the problem if we use ANSYS very well. But current quantum devices, NISQ, have noise and quantum limitations, so it might not be always outperform classical way. So this is a case studies for QAOA for max cut problems. So this is a data set provided, and this is a design from the paper I read. And optimization methods differs in gradient based or gradient free. And results were QAOA achieved 70 to 80% of the max cut value of the classical way, and circuit depths P when P is equal to 2, best trade-off between performance and complexity. So this is the most efficient one. And gradient-based optimizer were more faster than gradient-free, and so we conclude that further improvements in circuits and optimizations are needed to surpass classical methods, but it is kind of promising results for combinatorial problems. And this is second case using VQE and frequency allocation problem. So we wanted to assign frequency to base stations to avoid interference, ensuring efficient use of resources. But we wanted to minimize the number of different frequencies needed. So in this case, nodes represent base stations, and edges represent interference between stations. So approach was It is to convert the problem into a cost Hamiltonian based on graph representation and use the VQE to optimize the quantum circuit and classical optimizer examples Cobilla, SOSQP, LBGS. These are classical optimizers. Adjust parameters to minimize the cost function below. And classical methods like greedy or heuristic algorithms struggle due to the NP-hard nature of the problem. So we expected that it might be efficient if we used VQA very well. And this is a convergence for optimizers. Three classical optimizers were has the similar speeds and results optimal solutions found for 6-node graph require 3 frequencies. And we conclude that VQE provides effective frequency allocation by minimizing interference. So VQE may be suitable for addressing NP-hard problems in wireless communication. Oh, there is not. 아닌 것 같은데. 된 것 같아. So this is my presentations and these are references. If you have questions, just.
Non-environmentally optimization algorithm with a narrow need, right? Could you explain that a little bit?
잠깐, 그거는 추후에.
Okay, I have a question. Can you hear me?
I can hear you.
Okay, so I have a question regarding designing parametric quantum circuits at ansatz. Are there any general rule of thumb how to design ansatz in a particular way that exhibits the symmetry of the Hamiltonian? Like for instance, in quantum chemistry, we usually use ansatz called unitary coupled cluster, which natively reflects the excitation probabilities of the ground states given by the quantum chemistry Hamiltonian. So are there any general rule of thumb how to design ansatz based on the Hamiltonian given?
There are some 뭐라 해야 되지? 한국어로 답해도 될까요? 한국어로 답해도 될까요?
Yeah, sure.
그 안서치 관련해서는 제가 그렇게 많이 찾아보진 않았는데 혹시 그 드라이브에 올린 파일에 안서치 관련해서 그 하드웨어 에피션트랑 여러 개 종류가 있는 걸 혹시 참고하실 수 있을까요?
Okay.
네.
But as far as I'm aware, hardware efficient ansatz are for general problems and not specific to quantum chemistry or anything else. And I believe hardware efficient ansatz actually has issues with spanning too large subspace in the entire hyperspace. So it means you need a lot of memory and computational cost to perform efficient optimization with hardware efficient ansatz. So that's why I'm asking such questions. Okay, so thank you.
Any so SQRT to 엄동현 씨. If the problem is NPR but easy for VQE, what is the quantum complexity classification? 질문에 대해서 조금 더 설명해 주실 수 있나요? For calculus, we'll probably mention that. 아, 엄청 잠깐. 잠깐만요. 그 육도에 대해서는. 음흠.
근데 이제 퀀텀에서도 기초키 Q&A 뭐 피스펙스 이런 거
음흠.
그거 얘가 만약에 MP긴 한데
음흠.
이제 제가 VQ가 케이클링 같은 경우는 잘좀
네, 하는.
했으니까 그럼 컴플렉스 클래스가 퀀텀으로 따지면 어디에 속하니까
아,
그 얘기를 했습니다.
그 부분에 대해서는 조금 더 알아봐야 될 것 같습니다. 제가 읽은 논문에는 그런 얘기가 그냥 NP 하드라 나와 있고 그 케이스 스터디의 일환으로 한번 나와 있어서 그 부분에 있어서는 조사하고 다시 한번 발표를 하던가 이야기를 나눠볼 수 있으면 좋겠습니다. 네, fine.
Okay, I have one more question.
Okay.
So is the VQE robust to errors, like for instance, dephasing or depolarizing errors? Because recent studies are now showing that VQE answers that are especially designed specifically to address certain Hamiltonian is more susceptible to errors, meaning their performance degrades more steeply when there is error rates. So are there any general theorem how much VQE and such is like robust to errors in this era?
키위가 로버트 하던 얘기 하진 않아.
기본적인 전화 Q&A
음.
리스크를
네. 뭐라고 해야 될까요? 그 부분에 대해서도 좀 더 찾아보도록 하겠습니다. 질문.
고전 컴퓨터랑 비교해서 실험적인 평가밖에 안 되는지, 그러니까 이론적인 컴퓨터 비교 같은 게 가능한 건지 어떻게
지금 한번 해주시고
카이스트 측에서 그 이론적인 네?
실험적으로밖에 평가할 수 있는 건지.
컴플렉시티 비교가 가능한지 실험적으로 으로밖에 아직 안 됐는지에 대해서 질문을 하셨는데 애초에 VQA를 사용하는 것 자체가 실험적으로 이용하려고 쓰는 거고 왜냐면 그 아직 리스크 에러라서 이걸 쓰는 되는 이유가 있기 때문에 만약에 노이즈가 많이 없어지고 하드웨어적으로 많이 뒷받침이 된다면 저는 개인적으로 굳이 베리에이셔널로 써야 될지는 잘 모르겠어요. 왜냐면 그러니까 퀀텀 컴퓨터로 익젝트하게 그 회로를 만들 수가 있고 그 퀀텀으로 클래시컬한 건 다 만들 수 있기 때문에 그게 실험적이지 않은 게 의미가 있는지 저는 잘 모르겠습니다. 아, 이렇게 많아. Gradient Free Optimization Methods에 대해서는 어 그라디언트 프리 옵티마이제이션에 대해서는 되게 많은 example이 있어서 제가 그 하나하나 다 조사하진 않았습니다. 죄송합니다. 네, 질문 더 없으시면 끝내도록 하겠습니다. 들어주셔서. 오, 네. 발표 슬라이드는
발표 슬라이드 드라이브 올려놨어요.
네, 질문 없으시면 끝내도록 하겠습니다. 감사합니다.